Greetings, ladies and gents, and welcome back. It's Mike Maths and Science Club. In this video, we'll be starting a very important topic, which is actually work, energy, and power, which is actually a topic that is covered in term 2. Now, what I've done is that I've actually divided this. I've actually divided this topic into subtopics, into 3 actually subtopics. So there would be more videos to follow, 2 more videos to follow. But in this topic, we'll just be looking at work done, because everything begins with understanding work. If you understand work done, everything will cruise nicely. Right now, imagine you are 8 years old, and let's say you're driving with your brother, and let's say the car just suddenly switch off, and let's say for it to start, it would need to be pushed. Let's say that's our car there, right? And in this case, our car just switch off. That's a Mercedes Benz there. And suppose, let's say your brother, let's say for it to start, in this case it would need to be pushed. And suppose, let's say your brother says go do some work, all right, by of course by pushing the car. Now suppose, let's say you are there, all right, you are there pushing as hard as you can, struggling, in this case, but nothing is moving. So in this case, there is no, suppose, let's say there's no movement. Now in this case, you're pushing there, in this case sweating, it says sweating there, in this case tired, because you are trying as hard as you can to to push that car so that it can start, but in this case there is no movement. Now in this case, according to you, you did a lot of work there, but according to physics, you did absolutely nothing, zero work, completely unemployed in physics terms. Now you might be asking that, how is that possible? Because I'm sweating and my muscles are tired. Surely I did some work there. Unfortunately, you did not do any work, unfortunately. Why? Because in physics, work has a very specific meaning. Work doesn't mean effort. All right. In physics, we say that work is done only when 2 things takes place together: when a force is applied and the object actually moves. So in this case, we say that work is done when a force is applied, and in this case plus, and in this case the object moves. Right. So in this case, we say that in this case work is done when, in this case, when 2 things takes place: when a force is applied, and in this case the object actually moves. So we can say that in this case work is done when a force causes a displacement, when it causes the object to move. So if the force has an effect in the system, then we can say that in this case work is done, right? So in this case, that's the definition for work done. Now there's a formal definition, right, for work done according to the according to the guideline. Now, this definition from the guideline is kind of super confusing for me. It's very confusing. I don't want to lie to you, but this is what the guideline is giving us. So, according to what they want, this is the definition for work done. So they say that work done on an object by a constant force is equal to the product of the magnitude of the force, the magnitude of the displacement, and the cosine of the angle between the force and the displacement. Now, now that's the definition of work done according to the guideline. I don't want to lie, the level of confusion of this definition is on the highest level, right? For me, I don't want to lie, this thing is confusing. But mathematically, what they're simply saying there is that work is calculated by multiplying the magnitude of the force, the magnitude of the displacement, and the cosine of the angle between the direction of the force and the direction of the displacement. So in this case, mathematically, in this case, so work, which is represented by W, we say that work done by force is equal to, in this case, to the magnitude of the force multiplied by the magnitude of the displacement multiplied by the cosine of the angle between the direction of the displacement and the direction of the force. So in this case, that theta there would simply be the angle between the direction of the displacement and the direction of the force that you are actually trying to calculate its work done. Now, please note that we have many types of forces. So in this case, we have the applied force, the frictional force, tension force, normal force, and gravitational force. So as a result, what I'm simply trying to say there, ladies and gentlemen, is that as a result of the fact that we have different types of forces, so as a result, actually have also have different types of work done. So we have work done by the applied force, work done by the frictional force, work done by the normal force, and also work done by the gravitational force, and also work done by the tension. So in this case, we have also many types of work done. That's what I'm simply trying to say there. Now, let me just label what we need to know. So in this case, W there in this case stands for work done. Work done. Measured in this case in joules, and in this case force, that F there would simply be in this case the magnitude. Let me just write in another color. So in this case, this is the magnitude of the force. All right, and in this case that delta X there, which is so this simply be in this case the magnitude of the displacement. And in this case the theta there would simply be in this case the angle between the direction of the force of the displacement. Let me just write delta X there of the displacement, right, and the direction of the force, the direction in this case of the direction of the force. So in this case, that will simply be in this case our theta there. So in this case, that theta there simply in this case the angle between the in this case direction of the force. In this case, let me just finish my thought there. So this is of the force. Right. So in this case, the angle there, it's actually one thing that actually confuses a lot of people. So that angle theta there is simply the angle between the direction of the displacement and the direction of the force which you're trying to calculate its work done. Right now, suppose let's say I was pulling an object. Let me just make an example on this theta there, so that we don't get this confused at the beginning. So in this case, suppose let's say I was pulling an object to the right. So there's a wooden box there. I'm pulling it across a rough surface. Let's say I'm pulling it to that direction with the force, let's say of F of 20 Newton. I'm just bringing an example there. Suppose let's say the friction between, in this case, the surface in that box is actually, let's say 5, let's say Fk there. Let's say Fk is actually equals to 5 Newton. Right, and suppose let's say this object was displaced, let's say 5, let's say 10 meter, right, to the right. So in this case, so if they say that in this case calculate the work done by the frictional force. So in this case, what you simply do would say that the work done by the frictional force is equal to, in this case, to the magnitude of the force. All right, the kinetic frictional force multiplied by the displacement multiplied by the cos of the angle between. So in this case, our Fk there would simply be, in this case, the magnitude of the kinetic friction, which is simply the 5, multiplied by the magnitude of the displacement, which will simply be, in this case, that 10. And in this case, that's cos of theta. So that's theta there would simply be, in this case, the direction in between. So in this case, simply be the angle between the direction of the displacement, right, and the direction of the force which you're trying to calculate its work done. So in this case, remember that we said that this object is displaced 10 meters, all right, to the right. So in this case, simply be, in this case, the direction of our displacement to the right. So in this case, so we said theta would be the angle between the direction of the displacement and the direction of the force which you're trying to calculate its work done, which would be Fk there. So in this case, the angle between them would simply be, in this case, that theta there. So in this case, you would note that this would simply, so in this case, that angle there would simply be, in this case, 180. We know that, of course, angles on a straight line add up to 180. So in this case, if they are actually in the opposite direction like that, so in this case, the angle between them would simply be, in this case, 180. So this would simply be 180. So if you are trying to calculate, of course, the work done, all right, by, in this case, by the applied force, so this was going to be, in this case, the applied force multiplied by the displacement multiplied by the cos, right, of the angle between them. So in this case, this was going to be, in this case, 20 multiplied by 5. So that's actually 10 multiplied by 10 multiplied by the cos of. Now again, you do the same thing. So in this case, our object was displaced in that direction. So that would simply be, in this case, the direction of our displacement. And in this case, we also know that, of course, our force applied there is actually also in the same direction. It is actually in the same direction. So in this case, if they're in the same direction like that, the angle between them will simply become 0 degrees. So in this case, our angle there would simply become, in this case, 0 degrees. So if they're, in this case, in the same direction, so that would mean that, in this case, the angle there would simply be 0. So in this case, if they're, in this case, in opposite direction, the angle would be, in this case, 180. Right? If, of course, let's say we're trying to calculate the work done by the normal force. So let me just draw free body diagram first. So we have normal force. All right, we have normal force there. We have the force applied. Right? We also have, in this case, the kinetic friction, Fk. Also have, in this case, Fg. Right? So in this case, if I was trying to calculate, of course, the work done by the normal force, so in this case, what I was going to say there was to say that in this case, work done by, in this case, by the normal force is equals to, in this case, the magnitude of the normal force multiplied by the displacement multiplied by the cos of the angle between them. So in this case, simply, we know that, of course, normal force is on a horizontal surface is simply equals to mg, right? So this case, this simply become, in this case, mg, right, multiplied by, in this case, so this simply be multiplied by, you don't have to concern yourself about this one, ladies and gentlemen. So you can just simply say Fn, right, the, of course, the magnitude of the force there if you calculate it, and then in this case it will be multiplied by the displacement, which simply be, in this case, we say that's 10 multiplied by the cos of the angle there. So you notice that, of course, if we do the same thing that we did for this, right, so if we say that, in this case, so we know that, of course, the direction of our displacement is still in that direction, and we know that, of course, the normal force is actually upwards. So this would be Fn. So the angle between them, we notice there that those forces actually perpendicular to one another. So in this case, the angle between them would simply be, in this case, 90 degrees. So in this case, if it's, of course, if it's the force of gravity, again, you're going to do the same thing. So this I'm just, kind of going a little bit more on this theta part. So in this case, this is the angle of displacement. So if, in this case, if we were trying to calculate, in this case, the work done by, in this case, by Fj, so in this case, so simply, so the angle between them was gonna be actually 270. So this was gonna be 270. So what we are simply going to do, so in this case, this theta will simply be the angle between the direction of the displacement and the angle that you're trying to calculate its work done. So you must keep that in mind. So in this case, for example 1, there actually are 2 examples that I've kind of drafted there. So in this case, they say that a 6 kg block is pulled to the right on a horizontal surface by a constant force of 20 Newton. They say that the box experiences a constant frictional force of 3 Newton during its motion. The box covers a distance of 5 meters to the right. So So in this case, we know that, in this case, our object is displaced to the right. So in this case, the force there is simply 20 Newton. So in this case, we know that F there is simply, in this case, 20 Newton, right? We know that, of course, they also stated that the kinetic friction in this case is actually 3 Newton. So we know that, of course, Fk there is actually 3 Newton. Right now, they say that calculate the work done by the frictional force. So in this case, we would say that, in this case, work done by, in this case, by Fk equals to, in this case, Fk multiplied by, in this case, by displacement multiplied by the cos of the angle between them. So in this case, what we simply do there would be to say that we know that, of course, Fk is that 3 there. So in this case, simply become 3 multiplied by the displacement, which is simply that 5. So in this case, we have a 5 there multiplied by the cos. So in this case, again, that theta, we're going to do exactly what we did there. So in this case, simply become, so in this case, let me just write, yeah, it doesn't matter, even there it's fine. So in this case, this is the direction of the displacement, right? And in this case, we know that, of course, our frictional force is in the opposite direction, in that direction there. So in this case, simply become now Fk. So in this case, the angle between them would simply be, in this case, 180 degrees. So this will simply become 180 degrees. And if you put that into your calculator, ladies and gentlemen, what you're simply going to do there, what you're simply going to get is actually negative 15 joules. Now you must keep in mind that in this case, work done is actually a scalar quantity, right? So in this case, that negative there, it doesn't tell us about the direction of the of the work done, right? Because in this case, work done is actually it's actually we say that, of course, the work done is actually scalar quantity. So in this case, that negative there, it simply tells us that in this case, the kinetic frictional force was actually consuming some of the energy from the system, subtracting it. All right. So we know that, of course, the kinetic frictional force, it's always trying to, in this case, to resist the object from moving, right? So in this case, as a result, it would do actually a negative work done. So in this case, it will be so if it's negative, so that simply tell you that in this case, your force is simply, in this case, consuming, taking some of the energy from in this case, from your system there. So in this case, that negative is what what it actually tells us. So in this case, for number B, they said that calculate, of course, the work done by the applied force. We're going to do the same thing again. So we're going to say that work done by, in this case, by Fa is equals to, in this case, Fa force applied multiplied by, in this case, by the displacement multiplied by, in this case, the cos of theta. So again, we know that, of course, that force applied, that is actually 20 multiplied by the displacement, which is 5, multiplied by the cos of. So in this case, again, this is the direction of our displacement, right? Displacement is there according to our to the diagram there and what they said in the statement. And in this case, we can note that, of course, that that applied force is actually in the same direction. If they're in the same direction, we say that in this case, the force, the angle between them would simply be, in this case, 0 degrees. So in this case, if you put that into your calculator, you're actually going to get a value of 200 joules. All right. So in this case, simply be, in this case, for number B. Right. For number C, in this case, they say that calculate the work done by the normal force. You're going to say, in this case, now, so we're going to say that work done by the normal force, work done by the normal force equals to, in this case, the normal force multiplied by the displacement multiplied by the cos of the angle between them. Now in this case, yeah, that's fine, right? So in this case, remember that in this case, since this is actually a horizontal surface that we have here, so if I were to draw a free body diagram of that system there, of that box there, so in this case, I would actually have normal force, I would have force applied, I would have the force of gravity, and I would also have, in this case, Fk. So in this case, you notice that in this case, the normal force and Fg are actually equal. So in this case, if I were to calculate, of course, the normal force, we would know that, of course, on a horizontal surface, so we know that, of course, normal force is actually equal to mg, right? So in this case, simply become, this is our mass, which is 6, multiplied that by 9.8. So in this case, the answer that you get there would be the one that you actually put there. So in this case, I'm simply going to put this as, so this is 6 multiplied by 9.8 multiplied by the displacement, which is actually that 5 multiplied by the cos of. Again, we're going to do the same thing, right? So in this case, this is the direction of our displacement, this is the direction of our normal force, right? So the angle between them, that's actually a 90 there. So in this case, this is going to become cos of 90 degrees. Now, if you put this into your calculator, the answer that you're simply going to get is actually 0 joules. So in this case, this simply tells you that in this case, this force did not contribute any work, in this case, in causing that object to be displaced to, in this case, to the right as it was there. So in this case, that normal force, it did no work in this case, in helping this case the object to be displaced in that between that those points, between this case where it was and in this case until it was displaced that 5 meter there. So in this case, cos of 90, that gives us 0 there. Anything multiplied by 0, you actually get a 0. Right, so in this case, for the work done by the gravitational force, you're going to say that work done, right, work done by, all right, let me just say work done by, in this case, by Fg equals to, in this case, Fg multiplied by, in this case, by the displacement multiplied by the cos of theta. So this simply becomes, in this case, mg, which is 6 multiplied by 9.8 multiplied by 5 multiplied by the cos of. So in this case, again, this is our direction of the displacement. In this case, on our gravitational force is actually downwards there, so this will be simply be our Fg. So the angle between them there, that's actually 270 degrees. So in this case, simply become now 270 there. Right, so if you put that into your calculator again, you're simply going to get an answer of 0 joules. So that simply tell you that in this case, your gravitational force did no work in causing, in this case, that object to be displaced that 5 meter there. So for number E, they say that calculate the net work done. So in this case, when we say the word net, we are simply actually taking, in this case, the sum of all the work done, right, on the system, and we are simply just adding them. So in this case, we say that in this case, work done, the net work done is actually equal to, in this case, let me just use another color there. So in this case, the net work done is actually equal to the work done by the applied force, work done by the kinetic friction. So that's actually work done by, in this case, by the kinetic friction, plus the work done by the normal force, Fn, right, plus the work done by, in this case, by Fg. So in this case, what you simply do there would simply be to say that in this case, we know that the work done by the applied force, we got that to be 200. In this case, the work done by the kinetic friction, that was actually negative 15 plus 0 plus a 0. So these two just give us a bunch of zeros. Right, so in this case, if you put this into your calculator, what you're simply going to get is actually 108.85 joules. Right, so another way that you could have done that was simply, so in this case, was simply just to calculate the net force. So in this case, that W net would simply be the work done, by the net force. So in this case, by the net force, of course, in your system. So in this case, what you could have done there was to calculate the net force first. So you would have said that in this case, F net is simply equal to, in this case, now how many forces do we have in that horizontal dimension, right? Because in this case, our object was displaced in that dimension. So in this case, what I'm simply going to do would be to add these forces that I have there. Now remember that, of course, now we are dealing with forces, so in this case, I will simply need, of course, to add them, but in this case, in terms of course, of their direction. So in this case, simply be this case, W net simply be equals to, in this case, to Fk plus, in this case, the force applied. So in this case, our Fk, we know that that's actually equals to, we said that they said that's 3 Newton, but in this case, we know that, of course, our friction would be in that direction there. So what I'm simply going to do would be to take that direction as positive, so that direction simply be negative. So in this case, our kinetic friction simply be negative, and our applied force simply be positive. So this would be, in this case, negative 3 plus, in this case, the applied force, which was actually 20. Right, so in this case, if you put these 3 together, this 2 is actually going to get an answer of 17 Newton. So it is positive, so it tells you that in this case, your F net is simply in that positive direction, that's to the right. So in this case, what you're simply going to do would be to say that work done by the net force equals to, in this case, the net force multiplied by the displacement multiplied by the cos of theta. So in this case, we know that, of course, our net force there, they found that to be 17, multiply that by 5, multiply that by the cos of. Now, since, of course, you got that answer to be positive, so in this case, that will simply tell us that in this case, that net force there is simply to the right. So in this case, the angle between them, since they're in the same direction, so in this case, our net force there, so that's our displacement, that's in this case our F net. So in this case, the angle between them would simply be 0 degrees. So in this case, if you put that into a calculator, what you're simply going to get would be 108.85 joules. You're going to get the same answer, right? So it's that. So in this case, that would simply be for that example there. So there's a second example there which I'm being tempted not to do, but let me just look at it so that we can just try to to take as much information as we can. Right, now you have to forgive me for making this video a very long one. Right, but yeah, there's nothing we can do. So in this case, they say that Richard pulls a crate of mass 20 kg with the help of a rope up along the an inclined plane, as shown with a force of 270. So in this case, we know that in this case the force applied is simply 147. So they say that the kinetic friction between the crate and the inclined plane is 80 Newton. They say that the crate covers a distance of 12 meter up the incline. So in this case, we know that of course our crate was simply displaced 12 meter up the incline. So in this case, for 2.1, they said that draw a free body diagram of all the forces acting on the crate. So in this case, what you would do in this case, when they ask for a free body diagram, so in this case, you must give them the one without the components. So in this case, you would actually have, now we have the force applied, Fa there. We have in this case the kinetic friction, Fk. Say that there they gave us this case. So in this case, that simply tell us, suppose that that's actually a rough surface. So that would be Fk. Would have in this case the normal force, which is always perpendicular to your surface, and in this case we have gravity, which is always vertically downwards. So in this case, so this will be the diagram that you would give them. But in this case, when you are doing your calculations, you would need to resolve those to resolve that Fg, so that in this case it is in that horizontal, in that vertical, in that incline there, in this dimension, and in that dimension there, so that it's not outside, it's not at that angle there. So in this case, what you're simply going to do there would be to resolve those. So I'm sure you know how to resolve components. So in this case, we actually have the force applied. They actually have in this case Fk, right? But in this case, what you must note is that when you resolve Fg, so your Fg parallel will always be down the incline, right? So in this case, your Fg parallel will always be in this case down the incline, always. So in this case, simply be in this case your Fg parallel. So in this case, you'd actually have in this case your Fg perpendicular, and you'd also have in this case, you still have in this case our normal force there. So this would be the diagram that you would use in this case for your calculation. So this would be the one that you give them. This would be in this case for you. Right, so in this case, they say that calculate the work done by the force applied by Richard. Right, so in this case, what we are simply going to do there would be to say that work done by, in this case, by the force applied to simply be equal to the force applied multiplied by the displacement multiplied by the cos of the angle. Right, so in this case of theta. So in this case, what you must just keep in mind is that in this case, to calculate those components, to calculate mg parallels, in this case, we say that in this case, fg parallel is actually always equal to mg multiplied by the sine of theta. And in this case, fg parallel, fg perpendicular is always equals to mg multiplied by cos of theta there. So this is always the case, so you must just keep that in mind. So if I were to just calculate those components there, so in this case our mass that they gave us that to be 20, I had to multiply that by, in this case, now this theta and that theta there, they are not the same. So this theta here is actually the angle between our horizontal surface and that inclined there. So you must keep that in mind. That's not the same theta there. Let me just erase that. So that theta there is not the same. Right, so in this case, let me just represent it with beta, rather, so that we don't get confused with this. This will be 20 multiplied by, in this case, by 9.8, multiply that by, in this case, by the cos of the angle of inclination. So it's simply become, now say that's cosine 30. So this is, if you put that into your calculator, you're actually going to get 88 point, this case 98213 blah blah blah. So in this case, for this one, actually it's going to be 20 multiplied by, in this case, 9.8 multiplied by cos of 30. Again, you're simply going to get 174.56 and so on and so forth. So in this case, let's just calculate the work done by the applied force. So in this case, the applied force, we know that that's 147 multiplied, I think that's it, 147 multiplied by the displacement, which is 12, right? Multiply that by, in this case, by the cos of, again, we're going to do the same thing. The direction of our displacement is up the incline, and in this case we also know that in this case the force applied is also up the incline. So in this case they're actually in the same direction as the force applied and the displacement. So we know that of course the angle between them will simply be 0 degrees. So in this case, if you put that into your calculator, you're actually going to get 1764 joules. That is the work done by the applied force. So in this case, so for 2.2.2, they said that calculate the work done by the parallel gravitational force. So in this case, you're going to say that work done by, in this case, by Fg parallel simply be equals to Fg parallel multiplied by the displacement multiplied by, in this case, by the cos. That's actually the sine of theta. So in this case, simply become, in this case, so this will simply be, so Fg parallel, we found that to be 88.98213. You must put that, of course, you mustn't round that off early, right, if it's not the final answer, right? So this is, that's actually 88.98213, blah blah blah, right? So in this case, simply become now, so the value for the displacement, that's actually 12, multiply that by, in this case, by the cos of, so again, of theta. So in this case, our theta, remember, we have, in this case, so this is the direction of our displacement up the incline, and in this case our parallel gravitational force is actually down the incline. So that's our Fg parallel there, Fg parallel. So in this case, the angle between them would simply be now 180, right? So in this case, simply be 180 degrees. And if you put that into a calculator, what you are simply going to get is actually negative 1067.79 if you round that off joules. So this is to be the work done by the gravitational force, the parallel gravitational force, rather I should put it that way. So for 2.2.3, they said that calculate the work done by the kinetic friction. Now what I would suggest, you can just pause, try that question, and you can just play and just look at the solution. Right, I hope you tried it. So in this case, we would say that in this case the work done by Fk simply equal to, in this case, to Fk multiplied by, in this case, by the displacement multiplied by the cos of theta. Right, so in this case, what you're simply going to do, the Fk, they gave us that to be 18 if I'm not mistaken. So that's 18 multiplied by the displacement, which is 12, multiply that by, in this case, by the cos. Now again, remember, in this case that in this case we know that of course this is the direction of our displacement, and in this case we know that our friction is actually in that direction there. In this case, in the opposite direction. So this would be, in this case, our Fk there. So in this case, what you're simply going to notice that the angle between them is simply actually 180, simply be 180 degrees. Now if you put that into a calculator again, what you're simply going to get would simply be negative 216 joules. So that would be for 2.2.3. So for 2.3, they said that determine the net work done on the crate. Now you can do the same thing that we did there, right? You can do this, you can use this, right? So in this case, if you use that way, what you're simply going to do there would be to say, in this case, you're going to calculate Fnet first. So you'd say that in this case, Fnet simply be equal to, in this case, to the sum of the forces that you have, in this case, in the dimension, in this case, where your object is actually moving. Right, so in this case, you would notice that you'd say, in this case, you'd need to choose any direction is positive. Right, so in this case, you'd say this plus that, in this case, include. So if you choose upwards as positive and downwards as negative, so it would be, in this case, Fa plus, in this case, plus minus Fk plus minus, in this case, F G parallel there, and in this case whatever F rate that you're going to get there would be the one that you use to calculate, in this case, the network done. But in this case, what I'm simply going to do would be to say that in this case the network done, I'm simply going to add all of those work done there. It says if you say that network done is equal to, in this case, to the work done work done by, in this case, by the applied force, plus the work done by the kinetic friction, plus the work done by Fg parallel, plus work done by, in this case, by the normal force, plus work done by Fg perpendicular. Now what you must just keep in mind is that work done by perpendicular forces, in this case on your inclined, on your in this case on your system, is it actually give you a bunch of zeros. So in this case, what you're simply going to get, I don't know why am I keeping using that word bunch of zeros, but anyway, so in this case our applied force, we found that to be 1764, 1764, right? In this case, plus our kinetic friction, we found that to be 1767, 1007, that's actually 1067, 1067.79, if I'm not mistaken, just hope, right? So in this case, but plus minus, that's actually minus there, that's a minus, because in this case you notice that in this case have that as negative there. So in this case to be plus our Fg parallel, which I'm actually doing this the wrong way. Let me just erase that. So in this case our Fk found that to be negative 216, negative 216. And this is plus our Fg parallel, which is actually that 1000, negative 1000, and in this case 60, I think that's 64, so 67 there, 0.79 plus 0 there. Now if you put this into your calculator, what you're simply going to get there, ladies and gentlemen, would be, in this case, the net work done would be 480.21 joules. So that would be, in this case, the net work done on the crate. Now I'm simply going to end here. Now these are just the activities that you can try, so this would be the activity 1. You can try it. You can just send your answers. You can just post them in the comment section, and I'll just confirm, right? And also there's also another question there, which is activity 2. You can also just try that. So in this case, I'm simply going to end it here, ladies and gentlemen. Unfortunately, we don't want to make this a 1-hour video, even though I feel like it is already 1 hour. I don't know, right? So in this case, if you have got any question, you are more than welcome to just ask in the comment section. If you have in this case, if of course there's any topic that you would like me to cover, you are more than welcome to just also throw the name of the topic in the comment section, right? Of course, if this video helped you at some extent, be sure to like, and also if you haven't subscribed or follow, just hit that subscribe button and also that notification bell, so that when the other videos comes up, you'll be the first to be notified. But otherwise, ladies and gentlemen, as the story always ends, this is Sir Mike signing out. Sharp sharp.